Hello from Intellipaat. The topic for today is Apache Spark RDD tutorial. But before we begin, be sure to hit that subscribe button and click on that bell notification icon so you don't miss out on any updates from us. So firstly, we're going to be discussing what is big data, then the challenges that we face in big data analytics, a solution for that, what is Hadoop, then we get to Apache Spark, the features of Apache Spark, and then Spark RDD, which we're going to be discussing today with a tutorial, a little bit of hands-on, then eventually the actual hands-on part, the Apache Spark RDD tutorial. So without any further ado, let's get into what is big data. So firstly, in order to understand what big data is, we need to understand what is data. So data can be essentially of three types: structured data, semi-structured data, and unstructured data. Semi-structured data is the data which has some sort of an order but is not completely randomized as well, which isn't in the form of SQL tables but has keys and values assigned to those keys. Then we have structured data, which is in the form of SQL tables, where we have categories defined, the behavioral aspects of the data defined, and categories, the column names. And then we have unstructured data, which is seemingly random data, which doesn't have any order, like MP3, JPG. So these sort of data formats don't have any order or any categorical aspects to them unless we make categorical aspects from them. So what is big data? So now that we know what data is, we can now understand what big data is. So when we take extremely large data sets and computationally analyze them to reveal patterns, trends, associations related to the data behavior or what the data is exactly referring to, or the interactions that we see in that data, to basically reveal that sort of pattern or trend is basically what big data is, where we can use that data to understand what all of those things are. And then the examples for such big data is black box data, social media data. One of the most common ones is social media data, such as Facebook and Twitter, because we as users create accounts on these social media websites, and every second hundreds and gigabytes of data has been accumulated in these websites. Millions of people post things on social media. So all of this data is accumulated, all of this user data is accumulated, and the criteria is fulfilled for this data to be called as big data. And then other similar examples would include power grid data, transport data, stock exchange data, search engine data. So we search things on Google. A lot of people search things on Google every day, maybe millions and millions of people. So that sort of quantity, the magnitude of that, the sheer magnitude of the search volumes would constitute for data being accumulated on the Google servers, and that would be called as the search engine data, which is big data essentially. So there are 5 B's of big data. So in order to for any normal data set to be termed as big data, or any normal data source, data input to be termed as big data, it needs to satisfy certain criteria. Those are called the 5 B's of big data. So let us make sense of this. First V is velocity. So velocity means speed, and speed means the rate at which the data is being ingested or being input or being accumulated. So for instance, on Google, more than 3.5 billion searches are made per day. So as I was discussing before, search engine data. So say people are searching for particular things on Google every day in this much magnitude, like 3.5 billion searches are made per day at an average. So that is essentially equates to a lot of data being accumulated every day. So with a lot of speed as well. So 3.5 per day. So that amounts for velocity. The speed at which data is being accumulated is very continuous and very massive. So that is velocity. Then we have the most obvious aspect of big data, volume. So volume essentially means the size of the data sets that are being accumulated. So for instance, in the year 2016, the estimated global mobile traffic was 6.2 exabytes. For the entire year of 2016, the global mobile traffic was this much amount of data. So essentially the data set that is being generated by this is gigabytes and terabytes and exabytes in size. So that means that the data has to be really, really large in nature in order to be termed as big data. Then we have variety. So the data cannot simply come from a homogeneous source. Homogeneous source implies that the data cannot come from entirely one source, this big data. It has to come from multiple sources in order to be termed as big data. So say that I'm accessing certain amounts of data from a particular college website and certain amounts of data from the birth certificate database. So in order to combine those two data sets to create a full profile of a candidate or a student. So in order to do that, the data has to come from heterogeneous sources. so we can combine that data and form a larger data set out of that. And then we have Veracity. So there, in order to be termed as big data, when we are taking terabytes and terabytes of data, it is virtually impossible for that data to be perfect in nature. So we need to have certain inconsistencies in that data, as in certain values could be missing, certain values could be wrong. So those things are very normal, and in an ideal case scenario, we will never get data that is 100% perfect. So that accounts for veracity in data, the quality, accuracy, and whether the data is missing or not. So these factors essentially mean that in a practical world, we cannot have data that is perfect. So the another V for big data is called veracity as well. And then we have value, which is quite essentially the most important aspect, the most important V for any data to be called as big data, because the data needs to have value. You cannot have random gibberish in your data. You need for that data to have a certain amount of value. So what does value mean? So say when we are accessing a college database, there are certain attributes that matter and attributes that don't matter. For instance, if you are taking the primary key for every student, which is essentially the roll number or the academic number, so that amounts for data, that accounts for data, but it is not actually viable to use to create any model or to reveal any trends, because taking the roll number, taking the academic number of any student basically means nothing. It means nothing for the larger picture. So that basically means the value of the attribute of roll number in that particular data set is useless. So that doesn't have value. So as opposed to say something like grades, so we have grades or GPAs in college students. So those data values can be taken and converted into some sort of a module, converted into some sort of a statistic, because those data values are very important. So that way we need data sets where value is important. So that is the last V of big data and the most important V of big data as well, value. And then we move on to big data analytics. So now that we know what big data is, what qualifies for big data, we can move on to big data analytics. Big data analytics is the process of examining the big data to uncover trends, hidden patterns, statistical information, performing large calculations using that data. So basically when we have big data, the methodology which we use to analyze that big data in order to reveal those patterns or statistical information is called big data analytics. And as we can see, we have certain logos of certain companies here, the top tier companies in the world right now. All of these organizations, all of these sub-organizations as well use big data analytics in one way or the other. So ever since big data analytics has been implemented in these organizations, they have these methodologies have made a direct impact on profits, customer retention, targeted publicity and ads. So we will discuss that in the next slide. Big data analytics is an essential part of our day-to-day lives without us even noticing it. So say the first point is personalized customer experience. So what does that mean? Say you have an account on YouTube, you watch a certain category of videos. Say you're interested in computer hardware related videos. So if you keep watching computer hardware related videos, you will get those videos recommended in your feed. So how does that happen? That happens with the use of big data analytics. And then we have showing only of relevant data. So similar to the above point that I made, which means that it will only show you the data that is important to you. So if you're searching for something on Google, it will only show you the search results which are the most important, the most relevant search results related to that particular query based on other users, other consumers' interaction with that website. So that is another point another advantage basically of using big data analytics. Then we have the most important from a profit standpoint, targeted advertising. So say you only search for computer hardware related videos on YouTube, then Google will essentially start recommending you computer hardware related ads as well. So it will target that particular genre towards you. So that accounts for targeted advertising. And then we have research and technical analysis, which means that aside from commercial purposes, we also have scientific purposes, scientific intentions in order to get some modules, get check some hidden patterns related to climate change or weather or geography. So we can get all of that information with the huge amounts of data that is being accumulated related to the environment or related to scientific fields, and analyze that in research as well. So then we move on to the challenges that we face with the traditional big data analytics methodologies. First is hardware failure. So if we are using dedicated servers, dedicated hardware in order to analyze big data, there is obviously a possibility for that entire server to fail, or a hardware in that particular server infrastructure to fail, which would render our entire big data analytics system, big data analytics infrastructure useless. So say if you're having exabytes and exabytes of data with you, and a hard drive fails, that basically renders a lot of that data useless. So that, or if you're in the midst of processing a large amount of data, creating a model from that large amount of data, and there's a hardware failure, so all of that processing information is lost. So that is one of the problems that we faced with traditional big data analytics methods. And then we have combining of data. So when we are using distributed systems in order to store a large amount of data and process a large amount of data in parallel, for that regard, and then eventually to create a larger data set out of all of the analytics and computations that we did on all of the data values or all of the data sets, we basically need to combine them in the end. So combining them carries a large overhead on the overall infrastructure of your big data analytics system. So say that there are 99 disks, and we need to combine all of the data from those 99 disks, so that will take a large amount of overhead. So these are two of the most important problems, two of the most relevant problems that were being faced in the big data analytics field. So what are the solutions for these particular problems? The first solution that we came up with was a solution for the hardware failure, which was using the Hadoop distributed file system. So the HDFS essentially replicates the data on various nodes. So say you have a text file, and that is a large text file, a really huge text file. So you basically partition it into a lot of parts when you're actually storing it on a distributed file system. So the next step that you would do is essentially copy that data, create an exact replica of that data, and store it on all of the nodes, or as many nodes as you want. And by doing that, when one or two nodes fail, the entire data is still there, because you can access it from another node because you already made a replica of it. So that is basically data replication using the HDFS. That is something that HDFS does automatically depending on the configuration put into the HDFS. So that is one of the solutions using the HDFS. And the second solution is for combining of data. So Hadoop came up with a new methodology, which is MapReduce, which basically combines your data in a different way. So instead of you actually having to bring the data into your processing environment, you basically push the processing code, push the code that you're trying to implement on the data onto the node that you're trying to actually process the data at. So basically, instead of transferring large amounts of data from one node to another node, you're basically transferring the code, which is barely 500 kbs in size, to that particular node, and that node is processing that entire data. So this reduces the overall input-output overhead that is on the entire big data analytics infrastructure. So what is Hadoop? Now that we've discussed the solutions, we obviously need to know how Hadoop solves this using HDFS and MapReduce. So it is a platform that we use for storing big data, and it also helps us process this big data in parallel. So two essential factors essentially for this particular presentation that we have. It is used to store this big data in a very efficient manner with data replication and data partitioning on a distributed file system using commodity hardware. So what does commodity hardware mean? It essentially means that cheaper hardware. It doesn't mean that you have to create an entire server dedicated to storing your big data. You can use normal computers that are present inside your office and make them a part of a cluster, and a certain part of that node that you have, a certain part of that system that you have will be dedicated to your Hadoop cluster. So using a commodity hardware means that it is cheaper essentially in nature than creating an entire server farm or server for that. So the two methodologies that we discussed before in the previous slide were the HDFS and MapReduce, so we already know what those mean. And the goals, the requirements is basically abstracting and facilitating the storage and processing of large or rapidly growing data sets. So these data sets could be structured and non-structured, and we can essentially use simple programming models to process this data. So we basically, if somebody comes from a data analytics or data science background, you can basically go ahead and get started with big data analytics as well. You don't need to know any complex coding. You can basically know what normaling means or data science is, and basically implement that in Hadoop. And Hadoop does all of the management for the big data automatically for you, so you don't need to learn anything new specifically. So what is HDFS? It is a file system designed for storing very large files with streaming data access patterns running on clusters of commodity hardware. So we discussed what commodity hardware was, and then we have MapReduce. So we already discussed what MapReduce is. Also, it is a core component of the Hadoop ecosystem, and it facilitates the logic of processing. It is a software network and helps us process large data sets using distributed and parallel algorithms. And the parallel processing feature is the most important aspect of the MapReduce, because it helps us reduce the time in which big data is processed, because obviously if three nodes are running three parts of the same data in parallel, that would reduce the time significantly than all of those data sets being executed in a sequence. So it also plays a very crucial role in processing big data. So there are two essential components to the MapReduce. The first is the map, and the second is the reduce. As it says in the name, so the map creates key value pairs out of the data in parallel, independent of each other. And at the end of the mapping operation, when the mapping is 100% complete, all of this data is then reduced, which means that the data is aggregated, and we get our final output. So what is Apache Spark? So now that we know what Hadoop and HDFS and MapReduce are, we can now head on to Apache Spark. So we will not be dwelling into Hadoop and MapReduce much, because MapReduce is a significantly older technology, and now things like Apache Spark are used more. So basically what that means is, essentially in the past, hardware was really expensive. So we needed the functionality, the implementation of commodity hardware, where we basically wanted to push the code into the nodes that we were processing the code inside, so that we basically reduce the input-output overhead. But with Apache Spark and today's environment, where hardware is cheaper than before, we essentially don't need to concentrate as much on input-output overhead as we need to concentrate on the speed at which we process data. So what is Apache Spark? Apache Spark essentially is the framework that we can run on top of a Hadoop framework, which provides us with that speed. So how does this work? It is an open source clustered computing network framework for real-time processing. So it was introduced in UC Berkeley Research and Development Lab in the year of 2009. So it is recent in a way, although it's 10 years older, but it's still recent. And Apache basically acquired this, and it became a top-level Apache project by the year of 2014. And currently, Apache Spark is the most popular method, the most popular framework for big data analytics, and I'll tell you why. So the features of Spark include real-time computation and low latency because of in-memory computation. So what does in-memory computation mean? So essentially, rather than going to the disk and processing that data, we are basically bringing that data in our physical memory, or what we like to call it as RAM, and we are processing that data at essentially zero latency. Then we have generality, so we can combine the expertise of SQL, streaming and complex analytics. So if you know SQL, you can learn Apache Spark pretty easily. And then we have speed. So the reason we use Apache Spark essentially over MapReduce is because Apache Spark is 100 times faster for large scale data processing, because we are transferring the data into our RAM or physical memory. So the speed increases by 100% because the latency is virtually zero. And then the deployment. So if we have Hadoop or Yarn inside of the Hadoop as a resource manager, it's very easy to deploy as well. You simply need to have the cluster configured, and you can install Spark on it. And the rest of it is managed on its own. Then we have the ease of use. So if you are familiar with Java, Scala, Python, R, or SQL, so if you come from a development background, background like Java or Scala, or if you come from a data analytics background like Python, R, or SQL, you can basically get accustomed to Apache Spark pretty easily. And then we have powerful caching. So when we transfer memory, when we transfer data, we can cache that data, and we can access that data at a very short amount of time, in a very short amount of time. So that is powerful caching. So what is Spark RDD? So now that we know what the basic features of Apache Spark and what Apache Spark is, we can now move on to the Apache Spark RDD. So RDD stands for Resilient Distributed Datasets. So when we start up Spark, in Spark, basically it is the fundamental building block of Apache Spark framework, the fundamental data structure of the Apache Spark framework. So the RDDs are immutable distributed collection of objects. So they are immutable in nature, and each data set in an RDD is divided into logical partitions. So because we are using this on a distributed file system, the data sets that are present inside an RDD are divided into the logical partitions based on the division that is required on the different nodes of the cluster. And RDDs can contain any type of Python, Java, Scala objects. So basically RDDs are very easy to integrate with Python, Java, Scala objects, or R for that matter. So those are the benefits and what basically the general idea of a resilient distributed data set is. So now we will move on to the workflow of the RDD. So here we have on the left hand side, as we can see, RDD1 and RDD2. So they are combined, and there is a distributed acyclic graph. So basically we can see that there is a DAG scheduler, which means the combinations are then further combined, and then the combinations are further processed. There is a task set. The task set basically means that there's a cluster manager and there's a task scheduler as well. So the tasks are scheduled, jobs are scheduled in the order of the creation of the jobs, or in the order of basically the resources that are available. So these tasks are scheduled, and then basically when the scheduling reaches the point where the tasks have to be executed, the tasks are executed in the executor, where the threads and block manager are present. So the threads basically means the availability of the slots where the tasks would be executed, and the block manager basically means the combination on all of the nodes that are basically present within your cluster, where the data blocks are present, and the further combination, the further processing of the data occurs. So now that we know what the RDD workflow is, we will now move on to the type of RDDs that we have. So there are different type of RDDs. As per Spark source code, RDD is an abstract class having few methods. So there are not a lot of methods that are present in the RDD, but there are a lot of transformations that are present in the RDD, which is very important when we are processing big data, because we need to transform data a lot. So let us look at the different types of RDDs. So firstly, we have our parallel collection RDD, where we can see that we've created a value A. This is a Scala shell, by the way. We're using the SC, which is our Spark context variable dot parallelize, and there are two elements to it. So basically the partitions that are present inside of this value, inside of this RDD that we've created, are two partitions. So when we run a.partitions.size, we basically get 2. So that is essentially what it means. And then we have the next one is shuffled RDD. So a shuffled RDD is a RDD of key value pairs that represents a shuffle step. So we had a shuffle step when we use big data analytics, where all of the keys that are of the same sort are sorted when we are creating our final output. So basically a shuffled RDD implies that all of the values that are present inside the RDD are sorted by the key. So when we run dot sort by key on any RDD, for instance here in this particular example, we're running it on a variable M. They are basically sorted in order. We can see we have our particular sequence, one which is mapped to a particular value, and then we have 5 which is mapped to a particular value, so on and so forth. So basically what will happen is when we sort this particular data, it will basically sort it in the order of the ascending order of the keys that are present within the data set. And then we have our paired RDD. So the paired RDD basically means that these data sets, these RDD, are key value pairs, which are particularly helpful when we need to perform similar operations on keys, on each key. So for instance, here we have something like dot count by key. So what does that mean? So basically what we're doing here is we're running an operation where wherever there is a key, it is basically being counted and how many, in what quantity does that particular key exist. So here we can see we have 3, 7, 5, 4 and 2 as keys, and they have particular values that are mapped to those keys. So wherever there are values which are mapped to those keys, we see a 1. We see a mapped value which is 1 that is mapped to those keys when we run our dot count by key. But in the case of 2, we can see that there is no value which is mapped to that particular key. So 2 exists on its own without any mapped value to it. So in our dot count by key, we don't see 2. So that is because it has 0 values mapped to it. So that basically means that when we run the count by key operation, we get all of the pairs that are present inside of our RDD when there is no pair and there is no count that is to be displayed for that particular supposedly non-existent pair. Then it shows us the null value, which means that the value will not be showed in our final output when we run the count by key. And then we have our Hadoop RDD. So if we have our text file, if we have a Hadoop file or a sequence file for that matter, and we create an RDD using the Spark context, we can create an RDD out of that. So that would basically create a string value or a numeric value depending on the data type that is present inside of all of those files. We basically create an RDD out of the files that are already present or pre-existing in our disk. So we can basically copy that into our memory. And then we move on to the RDD operations. So basically we have certain operations that we can run on these RDDs. There are not a lot of functions, but there are certainly operations because we need to transfer this data. As you can see in the diagram, we can run a particular transformation on an RDD, and the action will occur after the transformation is run on it, and the value will be generated after that. So the thing about RDDs are that they are immutable because they are in memory. So they are present inside of the memory and they are not changed when we run a transformation on them. So basically what happens is whenever we run a transformation on an RDD, it returns a new RDD. So it is important for us to create a new RDD if we want to create a new RDD variable. Essentially, if we want to store the new RDD that we created, inside that variable we can store the new RDD. If we try to use the same variable again in order to store the new RDD, it will give us an error because RDDs are immutable in nature. So transformations are lazy operations on RDD. So lazy means that they are in-memory operations because we are not essentially altering the current RDD. Basically, we can set all of these steps up before we actually run our RDD transformation. So Spark knows what to do with that data and how to do it. So then we have certain transformations, certain examples of transformations, which we're going to be discussing some of in our hands-on tutorial section that we have later on. So map, flat map builder, map partition. So if you're coming from a data analytics or data science background, some of these terms might be familiar to you, like union, intersection, distinct, group by, key by. Even from an SQL background, you might be sort of familiar to this. So in Spark, we can run these same operations on RDDs as well. Now that we know the basic implementation and introduction of RDDs and know that RDDs work in memory in a certain way and they execute when we actually call upon operations that call for their execution and not during the statements that we make which set up the execution. Now we can understand how RDD works by a tutorial. So firstly, let us start our Spark shell. So you type spark -shell, enter. If you have your Spark installed, it will take some time to start up, and then we will see that the Spark has started with the sc context variable. So we can simply now create a list with a certain amount of partitioning, call this val x equals sc.parallelize. So the parallelize option gives us a way to create as many partitions as we want for our particular data that we are creating. In our case, we are creating a list with certain string values. So the first we'll call Spark RDD example, any values that you would want. This is just to show you guys how simple it is. If you are coming from from SQL or data science background to get started with Spark, sample example again. Then close this up. We can use the number of partitionings that I would want for this is, for instance, say 3, and close this up. And then when I press enter, our value X, our list, our RDD would be created. So as we can see, an RDD has been created of a string data type, and we can now go ahead and run new operations on this as well. So for instance, say I can run a map operation on this. So I can map all of these string values to a certain integer value. So say I want to create a new RDD, I'll call this Y, and I want to take X, and as I discussed before, create a new RDD out of X, because there is no way that we can actually transform X. We always need to create a new RDD and store it inside of a new RDD. So x.map, and that would mean that for every variable that is present inside this X, we can map a certain amount of a certain implementation for it. So say I want to map every variable that is present inside of the X RDD with 1. So I can simply type X, 1 and close this up. And when I press enter, all of the values that are present inside of X are now mapped with 1. So if we just see how this looks, so if we type in y.select to view our new RDD and press enter, so we can see all of the string values have been mapped to 1. So we can call this a key value, and this is a value. This is a key and this is a value, and they have been mapped together. So the mapping part of our operation, if we were doing a MapReduce operation, has been done. So next that I would like to discuss is a filter operation. So this is like or just a flat map operation. So what does a flat map operation do? So the difference between a map and flat map is the flat map converts even a multi-dimensional array into a single dimensional array, right? So let's see how does that work. So say that if we were running an operation such as this, sc.parallelize list, and create any list that you would want. I would create 1, 2, 3, a new an integer list with the values 1, 2, 3. And when I perform a flat map on this, simply type flat map, syntax sensitive, and the values that are present, the variables that are present inside this flat map, I would map them onto another list, a sub list, which would be x, x, and then perform a collect on this, so we can see what it looks like when I press enter. So as we can see, even though I'm mapping each of the values, that is 1, 2, and 3, to a list which should contain the values repeated thrice, it is not actually doing that. What it is doing is essentially creating a single dimensional array where the values that are there are occurring only three times. So that basically means that whenever we run a flat map operation on things, it basically doesn't create a nested array within that array. It creates a single dimensional array. So if we were running this for a simple map operation, if we just remove the flat from here and convert this into map, and then we press enter, so that would contain a sub list. So let's see how does that. So now we can see that for every X, when we are mapping it with a list, so what is happening is essentially all of the values that are present inside this list are being replaced by thrice repetitions of those values. That means 3 sub lists that are present within those particular value areas. So this is what the map does, and this is what the flat map does. So I hope that difference is clear. So now we can move on to certain SQL operations. So we have this ware option in SQL, right? So simply we have a similar implementation in Spark as well. We call it filter. So say if we create a list, we can call this list, let's create a list from here, and it's a numeric list, so something like this. Z, we call it numbers because we're going to be storing numbers inside of this, and within this list we can put in values such as 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, and then close up this list. and create an RDD, which we will call numbers. So say that we want to filter out only the even values out of this particular RDD that we have created. We can simply create another RDD for this. We'll call it events, and we'll put in something like numbers.filter. So that would filter out the RDD in the criteria that we would now write. So we will write underscore %2 equal 0. So once we do that and type in collect, it would basically filter out all of the values which has the modulus with 2 equivalent to 0. So whenever we are typing an underscore, that would include all of the values that are present inside of the RDD, and the modulus with 0 should be equal to 0. Modulus with 2 should be equal to 0. That is the criteria for even. If you've done programming before, you would understand that. And when we do collect, it would essentially show us all of the even values that are present inside of this RDD. So this could be any criteria that we would want. So if we could simply type in something like events odds, so that would create something like, and we type in not over here, so that would give us all of the odd values as well. So as we can see, 1, 3, 5, 7, and 9. So all of the odd values that are present inside of that RDD are there as well. Type it like union. First we have to form a union, and then after we perform the union, then after that we will type in distinct over here, and that is how it will happen. So first we need the full entire RDD that contains both of the values, and then we need to form the distinct. So that would give us the non-common values that are present within both of these RDDs. So when we press enter, so we will get all of the values that are not common within both of these RDDs, between both of these RDDs. Then obviously we can run something such as sort by. So how does sort by work? So now that we've created an RDD, we can simply type in something like this. We can use parallel for this, parallel.sort by, and then give a criteria for the sorting. So something like variable c, true. Select. When we press enter, we can see that the original array that we had for this for the parallel was 1 to 10, and here we also have 1 to 10 as well. Then we can use something like zip. So zip basically combines two particular RDDs in a different manner as well. So how does zip work? Say for instance, when we were using union, so that combined all of the elements that are present within both of the RDDs. What zip does is something in a quite different manner. So how does this work? So we'll see that. Firstly, let's create one RDD. We'll call it zip1, and create a list within it like 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, and press we will create another RDD with list 2, and create some other elements in this like 11, 12, 13, 14, 15, 16, 17, 18, 19, and 20. When we press enter, we'll create another RDD. So we'll create zip final and make it equal to zip1 zip, which is our RDD transformation statement, zip 2. So when we do that, it will create our zip final, which is the zip version of both of these RDDs. We simply type in zip final.collect to see our output. So we can see that the values that are present within both of those RDDs are mapped to each other in such a way. Like 1 is mapped, like here we can see 1 and 11, they are both mapped together, and 2 and 12, they are both mapped together. So basically in the sequence of their occurrence, the RDD values are mapped to each other. So that is what we can do with zip. So these are some of the few examples, some of the few things that you can do with Apache Spark. So you might be thinking, what is so special about this? Why can't I do this with simple Python? You can certainly do it with Python, but the thing about Python is Python on its own cannot process large amounts of data. So as much as I am doing this right now with a very small amount of data, like numeric data set that we have over here, Apache Spark's special quality is not in the methodologies that it provides. It is in the overall implementation and the background that it provides, like the in-memory processing and processing over a distributed file system. So all of these things, processing over a Hadoop cluster. So all of these advantages are done in the abstract form by Spark. So you don't need to worry about the logic of it all. You simply need to focus on the big data analytics aspect of things and not on the configuration, not on the distributed file system and any other aspect. So that is the main advantage of Apache Spark. So if you're interested in this, if you like what I showed you right now, you can simply try this on your own. Look at tutorials online, look at how to install Apache Spark. You can find it on our own website as well. You can basically will guide you through the learning path of Apache Spark in just a moment right now. So if you head over to Intellipaat.com, you will see our website right over here. So if you want to learn Apache Spark in a much more organized and structured format, where you know what to learn, when to learn it, and in what magnitude you need to learn it, you basically need to go over to Intellipaat.com to have a look at one of our courses. If you're interested in going forward with Apache Spark as a data analytics, as a big data analytics tool, simply type in Spark in our search box over there. Click on search. So here we can see we have a lot of courses that are available for Spark depending on the criteria and need that you may have. So for people who want a shorter course but with Python, we have PySpark training course. If you're accustomed to Python and you want to start your big data analytics career using Python, you can certainly go for the PySpark training course on its own. Then we have our Spark Master course, which contains all topics that are related to Spark, which is something that we will be discussing right now. So if you simply open up our Spark Master course, so here we can see we are on the page of our Spark Master course. So the special part about our course is that our course is in collaboration with IBM and Microsoft. So the certification programs that IBM and Microsoft provide have endorsed our course as well. So here we can see the classroom training is available for Apache Spark and Scala for our Spark shell implementation of things. Then we have PySpark, the Python and Java. So why are Python and Java important? If you're going to be learning PySpark, you need to know Python, and if you're going to be learning Scala, you need to be aware of Java as well. So Python and Java and PySpark are the courses that we provide with this. The primary part is the Apache Spark and Scala. So as we can see, the key features of this course, we can see over here, is that there is 240 hours of instructor-led training, which means that you will be seated in live classes, live online classrooms, and you can basically ask your instructor wherever you have a doubt during our live classes. So 240 hours worth of that content. Then we have 190 hours worth of self-paced videos. So in total, we basically have videos that amount to 190 hours. So if the instructor is not going according to your pace, if you want to learn new things, if the instructor is going too fast, you can basically look at our self-paced videos as well to do the course at your own pace, and then ask the instructor any doubts that you may have accumulated during your self-learning period. Then we have 480 hours worth of project work and exercises. So basically we provide you with hands-on and project work related to the course, which amounts to more than 480 hours in this particular Spark Master course that we have. And then we have certification and job assistance for that. So basically, what does that mean? Once you've completed the course, once you've satisfied the criteria for course certification that Intellipaat provides, you can be assisted with jobs. Basically, your resume could be forwarded to potential companies and organizations, and depending on how you perform in your interview, you might land that job as well. We have a flexible schedule. So we're all IT professionals with scheduling conflicts. So if, say, you have a scheduling conflict with our class timings, you can certainly skip that class, and you could be seated in another batch and attend the same class again and ask your doubts live online. And then we have a lifetime free update. So if, say, there is a significant technology update in Spark or Java or Python or PySpark, any of the pertaining course material, if there is a significant update which makes the technology much better or much faster, we upgrade our courses as well for absolutely free. So you can come back and visit our course anytime. So the upgraded material will be there as well. And then we have 24/7 lifetime support and access, which means if you're facing any technical issues or any scheduling queries, you can contact us anytime. We would be happy to help you in that regard as well. So if we go over to the course learning path that we have. So the following concepts would be covered: pattern matching, Scala collections, RDDs in Spark, which we just discussed a little bit of. Data aggregation with pair RDDs, a complex topic in Apache Spark. MLib, so we have MLib as well, which is the machine learning library that Spark provides, which we can implement with Python as well. Apache Spark and Big Data, RDDs and frameworks, Apache Spark, data frames, and PySpark SQL. So a really beneficial course if you're coming from a Python background. Flume and Apache Kafka. So real-time analytics using Flume and Apache Kafka, and you will understand how to implement that using Apache Spark. Then we have libraries such as NumPy, SciPy, and Matplotlib. So if you're from a Python background, if you're not from a Python background, you can certainly be taught how to use NumPy, SciPy, and Matplotlib, which can be integrated with our PySpark. So we can basically perform all of our NumPy, SciPy, and Matplotlib operations with big data sets using the Spark implementation that Python provides, which we call as PySpark, and then Python WebStream. So who can sign up for the Spark training? If you're a big data analyst, a data scientist, analyst, researcher, IT developers, ETL, data engineer. So all of these job profiles we cover as well. This could pertain to you as well if you're looking to enroll in a career of big data analytics particularly. And so we have our testimonies right over here as well. So you can listen to our customers' testimonies as well related to if how much beneficial these courses have proven for our customers. And you can look at our course content in detail. If you want to know what exactly we would teach in our courses. Even if you're not opting for our courses, you can certainly look at the learning curve, the learning path that we have over here, and certainly try to follow it in a way where you would learn all of the topics that are covered within the Spark framework. So that brings us at the end of our session. But before we go, we have a special offer for you guys. If you use the coupon code YouTube30 for all of our YouTube audiences watching here today, if you use the coupon code YouTube30 on Intellipaat.com on any of our courses, you will get a flat 30% discount on all our courses, regardless of what the course is, not just the Spark courses. You'll get it on every course that we have, a flat 30% discount. Just use the coupon code YouTube30 for that. So that is about it for the session, guys. If you want to contact us, you can certainly contact us using the following contact details present on your screen right now. I'll leave it on the screen for you guys. As for now, goodbye from Intellipaat. Hope to see you again next time.